Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 6, 2026, about 6 days ago. It presents a new framework called MMFormalizer, which appears to be the first method capable of formally translating advanced physical theories, like quantum mechanics and relativity, directly from multimodal inputs. The paper is titled MMFormalizer, Multimodal Autoformalization in the Wild. And, as we'll see later, this approach enables frontier models like GPT-5 to bridge the gap between visual perception and rigorous mathematical verification in ways we haven't seen before. Figure 2 illustrates this dependency structure for classical mechanics. It maps how high-level principles, specifically Newton's 3 laws on the left, decompose into derived concepts like momentum or the Hamiltonian formulation. Notice the color coding. The brown nodes represent complex entities the model must synthesize, while the green nodes, such as time and space-time basis, represent the grounded primitives where the recursion terminates. This visualizes the paper's core idea of recursive grounding, because every physical abstraction is eventually anchored in a fundamental, dimensionally consistent axiom. Turning to the evaluation, Figure 1 summarizes the performance of 5 representative models on the benchmark. The left radar chart measures compilation accuracy, while the right chart tracks human verification. You can see from the expansive purple region that GPT-5 dominates in physics tasks, particularly in mechanics and modern physics, where it reaches near-perfect scores. By contrast, Gemini 3 Pro, shown in orange, is strong in geometry but notably weaker in those physics domains. It is also worth noting that synthetic geometry, located on the far left axis, remains the hardest challenge for every model tested. Figure 3 now details the complete 4-stage pipeline. It begins on the left with the multimodal input, processing both text and a visual diagram. Here, a charge in an electric field. Next, the recursive grounding phase decomposes the problem into a concept tree, using the termination condition to decide when a concept is fundamental enough to stop. Then, axiom composition matches these concepts to formal theorems. Finally, the semantic check on the right verifies that the output matches the original intent. Alright, having walked through the method, Figure 4 breaks down the benchmark dataset itself. This chart details the distribution of the 115 problems in the PhiXAF suite. You can see that MathVerse, the top bar, makes up over 50% of the data, focusing heavily on solid and plane geometry. Below that, the Phi6 dataset contributes roughly 22%, introducing complex physics domains like quantum mechanics and thermodynamics. This mixture ensures the model is tested on both pure mathematical proofs and applied physical reasoning. With the dataset defined, Table 1 presents the detailed performance breakdown across all 4 domains. The results compare frontier models in the top section against open-source baselines below. Looking at the PhiX columns in the center, GPT-5 stands out with over 70% compilation accuracy in modern physics and mechanics. By comparison, Gemini 3 Pro dominates the MathVerse section on the left, hitting perfect scores in the function category, but lagging in physics. Finally, the open-source models at the bottom struggle significantly, often failing to compile any correct physics solutions at all. So, while Table 1 showed the final scores, Table 2 performs an ablation study to isolate which components actually drive that success. This table tracks metrics like compilation accuracy and graph depth when specific features are turned off. Crucially, look at the section labeled Ablation on Grounding with Image. In the electromagnetism column under PhiX, the accuracy drops from the original 100% down to 50%, proving that visual input is essential for inferring hidden physical constraints. We see an even sharper drop in the ablation on synthesizer without code road just above, where the same score crashes to 0, showing that reference code is vital for generating valid formal statements. Wrapping up, MMFormalizer marks a significant leap by successfully extending formal reasoning into complex domains like quantum mechanics. Its recursive grounding framework ensures that abstract physical laws are strictly anchored in visual evidence, paving the way for verifiable scientific discovery by artificial intelligence. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.